Okay, so in this video I want to continue practicing finding limits analytically. And remember this idea here. If the limit that you're trying to take, if that function that you're looking at has a hole or a removable discontinuity where you want to take the limit, then you just try to figure out a way to fill in that hole, and then you can just plug in the value at that point. So I'm going to put this down here. Okay, so there's the main strategy again. All right. So let's look at this new function that we have. It's definitely not continuous at 0. So let's see if we can come up with a function that is continuous there, that looks just like this one. So the way to get functions that look just like that are to multiply this thing by different forms of 1. So let's write this out. Limit as t goes to 0 of the original function, t squared plus 9 minus 3 over t squared. Now, I don't really know what to do with that other than normally you try to get a root out of the denominator. So let's actually get the root out of the numerator because I don't really know what else to do. So t squared plus 9 plus 3, the conjugate of the numerator. Okay, so if I multiply out the numerators, then let's first put the limit down. So as I multiply out the numerators, I'm going to get t squared plus 9 on top when I square the tops, the first two terms. And then when I multiply 3 times the root and then negative 3 times the root, those guys will cancel. And then I have negative 3 times 3, which is negative 9. And then on the bottom, I'm just going to leave this in factored form, because maybe eventually something will cancel. Right? Yeah. Okay. So then on top, the plus 9 and minus 9 will cancel. And so I'll just get t squared over t squared root t squared plus 9 plus 3. Right? And so this graph has a removable discontinuity at t equals 0. And so what we can do is we can say now, then something that'll fill in that hole at 0 will be to cancel those t squareds, and I'm left with 1 over root t squared plus 9 plus 3. And at that point, now I've got a function that actually is continuous at 0 because I can plug 0 right in there. So this is just going to be 1 over square root 0 squared plus 9 plus 3. So that's 1 over 3 plus 3, so 1/6. And then that's it. That's it. Let's see. Let's try the next one. So now the idea is that you look at this thing and you don't intuitively know right off the bat if this thing's even continuous at x equals 4. And if it is continuous, if it's not continuous, how do you know that it's a hole versus like a jump? How do you know it's not this versus this? So if you don't know, then you just test each limit by itself. You test what happens to 4 from the left side of f of x, and then you test what happens to the right side of 4 for the y values. So when I'm on the left side of 4, that means values like 3. That means that I'm using this part here. So I'm looking at the function 8 minus 2x. Right? Well, 8 minus 2x from the left side of 4, it's really just going to get really close to the value of 8 minus 2x when I plug in 4. And so that's going to be 8 minus 8, which is 0. So now I know that when I get close to 4 from the left side, this function is going to be close to 0. Right? And actually, since it equals 4 there too, we could even fill in that dot. The other function from the right side, or the other part of the function, That uses the other equation because that's for x is greater than 4. So it's this, x minus 4. And I know that square root of x minus 4 from the right side, in fact, if you think about what this graph looks like, it looks like this. And I'm only approaching it from the right side. So I can say that that's going to be 4 root 4 minus 4, which is 0. And now I know that these two guys are the same. So yeah, this line here says that as I approach 4 from the right side, I also get 0. So since those two limits are the same, so since the left hand and right hand limits are equal to 0, we can say that the limit as x goes to 4 of f of x, that also equals 0. Okay? Notice it doesn't really matter what happens at 4. It turns out there could just be a hole right there, and that would be fine too. Okay, let's look at 7. 7, this one really could go down here under a couple trickier examples. 7, it's the absolute value of x over x. So there's definitely a discontinuity when x equals 0. I just intuitively, right off the bat, I'm not sure what kind, let's say. You could graph it and then figure out it's a jump, but you don't have to graph it to figure that out. You could just analyze it algebraically. And so let's look at the one-sided limits, right? And the positive one, so coming at it from the right side. Well, coming at it from the right side is probably the easier one to analyze. That means that I've got a positive number divided by itself, right? A positive absolute value, which is still positive, divided by another positive version of itself. So that's got to be 1. Okay. Whereas over here, the 0 from the left side means I'm plugging in really tiny negative numbers. If I plug in a tiny negative number on top, I've got a positive version of it. But then I got to divide it by the negative version of it. So I've got a positive number over the negative version of itself. So that's going to be -1. So what this says is that around x equals 0, if I come at it from the right side, I have a value of 1. If I come at it from the left side, I have a value of -1. And so there's definitely no way that this is continuous. So it's got a jump discontinuity there. But this is all just gravy. Really, all this tells you, all that you needed from this, we're trying to figure out what happens right at 0, or right around 0. Well, it does two different things there, so you would say that this limit does not exist. Okay. I'm going to stop there and make another video for the trickier examples.